Good morning, ladies and gentlemen, and welcome to a new video. Today we're going to be discussing chi-squared goodness of fit test. This is unfortunately a topic that was removed from the curriculum because of the schools closing down, but it is typically covered in a proper AP statistics curriculum, and therefore we're going to talk about it today. Of course, brought to you by Couch Potato Brand Snack Food and Beverages. We sell food and beverages, nothing more. Yeah, so that statement says it all. They're a food and beverage company, and wow, are they the best at it? That's all I've got to say. They're good. They're good. All right, so let's look at just an example that motivates what a goodness of fit test does. Now, obviously, that's not really great grammar, goodness of fit, but that's the name of the test. And so that's what I'll be saying throughout this video. So here's an example. In 2018, Couch Potato Brand Snack Foods, under the previous marketing regime, announced the following color distribution of their colorful Couch Potato Candies line of snack foods. So in the entire population, there was supposedly 30% brown, 20% yellow, 20% red, 10% orange, 10% blue, and 10% green. All right, so that's what they are saying was really the population's distribution of colors of these candies. Now, just looking at this data, hopefully you're realizing that this is categorical or qualitative data, right? Each candy itself falls into one of these 6 color categories, right? So the data that is being presented is categorical or qualitative. Now, you might remember earlier in the year when we were studying qualitative or categorical data in hypothesis tests, we did, either a 1 proportion z-test, 2 proportion z-test, or maybe we built a confidence interval around these values. So this is similar in that we're going to be dealing with proportions, but the difference is the proportions that we deal with today are not going to simply be like a success failure. Okay, and you'll see what I mean. And so since the proportions that we deal with today are not just success failure, we can't just use the simple 1 proportion z-test, 2 proportion z-test. Okay, we need to build something else, another type of hypothesis test, and that is the chi-squared goodness of fit. So continuing on, in 2020, my bag of colorful couch potato candies had 12 brown, 7 yellow, 8 red, 8 orange, 7 blue, and 8 green. So I have this one sample of these candies, and you can see the count or the frequency of the colors within my bag. All right, so this information is now your sample information. That's your sample data. And of course, we can convert it to sample proportions or p-hats. But the question we're going to try to answer is there evidence based on my bag of candy that the color distribution has changed under the new marketing regime? So how do we test this? Well, the question we're going to ask is the following. Does my sample distribution of colors fit good with the population distribution of colors? Do our distributions fit good with one another? Obviously, again, horrible grammar, but that is the name of the test, so I will continue saying it that way. All right, here is our plan. So this is going to be a proper hypothesis test, but of course, I'm going to have to introduce a whole new type of distribution, which I'm sure you have guessed already. It's going to be called the chi-squared distribution, because we can't use the normal model because this is not a simple success-failure situation. There are many different categories or many different colors that each individual candy can fall into. Again, it's not just a success-failure situation. So the population of interest is the true color distribution of the 2020 colorful couch potato candies. We were given a 2018 population distribution, and what we're wondering is, do we have evidence that the 2020 population distribution is different than that 2018? And we're going to see if my sample fits good with the 2018 population. But first, a null hypothesis. So remember, in previous hypothesis tests, we basically assumed status quo, right? So we assume that nothing has changed. And that's going to be the same thing here. We are going to assume that the true proportion of brown is 30%, the true proportion of yellow is 20%, the true proportion of red is 20%, so on and so forth. So you might be thinking, okay, that's going to be a lot of writing. So you might say P subscript B for brown is equal to 0.3. P subscript Y for yellow is equal to 0.2. P subscript R for red is equal to 0.2, so on and so forth. You might express the null hypothesis this way, but rather than, look, we only have 6 different proportions here in this particular case, but what if you have 30 or 40? Then this could be a little bit cumbersome. So rather than write the null hypothesis this way, one option is to say the following. The 2020, color distribution is the same as the 2018 color distribution. Okay, well, if that's your null hypothesis, then what do you think the alternative hypothesis is? I'll give you a second to think about it. All right, assuming you maybe paused the video and thought about it, the alternative would just be that at least one of these color proportions are different. We don't necessarily need the whole thing to be different. If at least one of these colors, one of these color distribution proportions is different, then that means the null hypothesis is false, right? So that's going to be our alternative. At least one of the 2020, did it again, 2020 proportions is different than 2018. All right, so that's typically how it's done with the chi-squared test. Our hypotheses are written in words. Okay, let's discuss now how to obtain a test statistic, because of course that is the piece of information that we need in order to calculate a p-value, which we will then compare to an alpha value to make a decision. So as far as hypothesis tests go, this is identical in nature to how you would run any other hypothesis test that you've seen thus far. We're going to find a test stat, and we're going to, from there, calculate a p-value, and then from there, we're going to make a decision on the null and the alternative. Okay, the only difference is we can't use the normal model as discussed earlier. So let's first discuss how to calculate our test statistic, and then we'll talk about the distribution that we will be using to calculate the p-value. So in our situation, we have an observed amount of data, and then we're going to fill in what we expected to see based on the fact that we are assuming the null hypothesis is true. So of course, we observed the following counts or frequencies of the colors in my bag of colorful couch potato candies. There were a total of 50. What do you think we would have expected though? So I'm going to take a moment, or I want you to take a moment and think about how we might fill out the expected count column. So take a moment and think about it. Okay, so the way we are going to calculate the expected count is we're going to take the total from my sample, so the total count from my sample, and we're going to multiply it by what we are assuming is true about brown, and that is that we are assuming that 30% of the candies are going to be brown, as was reported by the company. So we will multiply this by 0.3. Similarly, for yellow, we're going to take the total, 50, and multiply it by what we are assuming to be true, which is 0.2. All right, I'm going to fill out the rest of this chart in the very same way. So let me pause recording. Okay, and so this is how you would calculate this column. I am now going to go ahead and actually write the counts. Okay, and there you have it. So these are the expected counts based on the null hypothesis and assuming that it's true. One check that you can do is to make sure that your total in the observed and expected count columns are both the same. All right. And in this case, they are, so we're good to go. Now, this last blank column, this is what we're going to use to calculate our test statistic. So what we're going to do for each row is we're going to calculate a value called a chi-squared value. Right, so that symbol that you see there is chi-squared. It's spelled C-H-I. It's not pronounced chi, it's pronounced chi. And it looks like an X, but it's kind of like a squiggly X. Anyway, that's the symbol that we use for this letter and for this distribution, chi-squared. Now, you'll notice that the observed column and the expected column are not exactly the same, but that's fine, right? We've seen this so many times. Our sample is never exactly what we would expect if H null is true because of something called sampling variability. So we know that we anticipate some sort of differences, and that's fine. So just because observed and expected are not exactly the same at this point, that does not, of course, prove that H null is false. What we want to see is, are the observed counts very different or significantly different from the expected counts? Okay, and so in order to do this, we have to first calculate something called the chi-squared value. For each color, we will do the observed minus the expected. We're going to square that term, and we're going to divide by the expected. Right, and so for each one of these individual colors, they will have their own chi-squared value. The reason, so essentially what it's doing is it's sort of measuring how different the observed values are from the expected. And the reason that we're squaring that numerator is because if we did not square the numerator and we ended up adding all of the chi-squared values up, then we'd get a sum of 0 because there is as much difference below as there is above when we're comparing observed and expected. And that will always be the case. And so if we did not square that numerator, we'd always get a sum of chi-squared values of 0, which would not be a useful piece of information. So that's the reason for squaring that term. All right, I'm going to go ahead and fill out this column, and I'll be back in just a moment. Okay, so that last column is filled out, and as you can see, in this last cell, I've summed up each color's chi-squared value. And this sum of all of the chi-squared values is our test statistic. So we call this the chi-squared test statistic. And this is the value of importance. This is the value that we're going to use in order to calculate our p-value, of course. All right, now take a moment and think about what the chi-squared distribution might look like. Consider the fact that what we're doing, what the chi-squared distribution is it's a collection of all possible chi-squared values. So it's, or I should say, a collection of all possible sums of chi-squared values. So in this particular sample, we observed a chi-squared value of 6.3. But if I opened up another bag of the couch potato colorful candies, I might get different observed counts and therefore different chi-squared values and therefore a different test statistic. So think about the types of values that the chi-squared test statistic can take on, and take a moment and think about what this distribution might look like. All right, so now assuming you have thought about it, I'm going to scroll down and show you what the chi-squared distribution does look like. One thing that I really hope you picked up on is that chi-squared test stats cannot be negative. At best, the best possible chi-squared test stat you could get in terms of, evidence that H null is true would be if the test stat is equal to 0. Think about what that would mean. That would mean that each observed count and each expected count for their respective rows are exactly the same. So the smallest possible chi-squared value is 0. And then, of course, if these things are wildly different, in theory, the chi-squared test stat could potentially be infinity. Right? So the range of possible values for your chi-squared test stat is from 0 to infinity. And assuming H null is true, it should be no surprise that most of the chi-squared values should be lower numbers. And then as the chi-squared values increase, the distribution's area starts to also decrease. So it's less likely to obtain a large chi-squared value, assuming, of course, H null is true, right? That's the whole idea. So if we end up getting a large chi-squared value, then that will be evidence that the null hypothesis is actually maybe not true and should be rejected. All right. So hopefully you can see now how we might calculate a p-value. So let's go ahead and one other thing that I want to mention about the chi-squared distribution is it does depend, the way this looks does depend on the number of possible values of the category that you're studying. So here with color, there are 6 possible colors, right? Well, that being said, maybe 6.3 is a large number in terms of chi-squared test stat. But what if there were 1 million colors? If there were 1 million colors, that means we're summing 1 million numbers together. And if we end up with a chi-squared value of 6.3, that might not be so big, right? If you sum 1 million numbers, 1 million positive numbers to get 6.3, that means you have a lot of numbers that are very close to 0, right? So saying that 6.3 is a large test stat or a small test stat it depends on how many numbers you're summing together. And so that's where degrees of freedom are going to come into play. So let me show you an example of that in just a moment. All right, so these are chi-squared distributions with varying degrees of freedom. Degrees of freedom, by the way, oops, let me go back to the regular pen. Degrees of freedom is equal to n minus 1, where n is the number of values of the categorical variable that you are studying. So the number of possible values that that variable can take on. So in our example, there are 1, 2, 3, 4, 5, 6 possible values that the variable of color can take on. And so in our example, degrees of freedom will be 5, which is, of course, 6 minus 1. Now, anyway, as you can see, as the degrees of freedom increases, it becomes less likely to obtain lower values, right? When degrees of freedom is 1, it looks like that much of the data, let me go back to, let's see a highlighter. Looks like that much of the data is between, or much of the samples will give you something between 0 and 1 in terms of your chi-squared value, right? That's with a low degrees of freedom. But let's go back up to the degrees of freedom of 10. Look, very, very little of the data, in fact, almost none of the samples will give you a chi-squared value between 0 and 1 or 1 and 2. All of a sudden, it becomes more likely to get larger chi-squared values. And that should make sense because you're adding more numbers together. The more numbers you add together, the more likely it is to get higher chi-squared values, even if the null hypothesis is true. Because sampling variability is a thing, and so it's always going to, it's just extremely unlikely to ever get exactly what you expect in a distribution, in a categorical distribution of proportions. All right, so there we have it, and hopefully this gives you a little bit of insight into how we calculate the p-value, and that's what we're going to discuss next in just a moment. Okay, so I've gone to the more generic chi-squared distribution, and I've placed our test statistic there. Now, take a moment and think how you might use this distribution to calculate the p-value. So, assuming you paused and gave it some thought, well, maybe you thought, all right, well, in order to calculate the p-value, I'm going to say, well, what's the probability of obtaining a chi-squared value that is equal to 6.3, which is a reasonable assumption because that's what we observed, and we're wondering, well, what's the probability of getting what we observed? Again, of course, assuming H null is true. Well, as we know, if we have a continuous distribution, which is what we're looking at, a continuous distribution. The reason is that our chi-squared variable can take on any real number between 0 and infinity, theoretically. So this is indeed a continuous distribution. If we try to calculate this probability, we're just going to get 0. All right, so this won't help us. Instead, what we're going to do is we're going to ask ourselves, what's the probability of obtaining our test statistic of 6.3 or greater? Or you might say, or more extreme, right? That's always the question we ask. What is the probability of obtaining our observed sample or more extreme? Now, in this example, the more extreme is always going to be just greater than, because, of course, as we mentioned, we cannot get negative numbers, and numbers near 0 indicate that we have a sample distribution that is fitting very good with the population distribution. So the question we're always going to be interested in is, what is the probability of obtaining that observed value or greater. Right, and it's just as simple as that. So let's go ahead and calculate this using the TI-84. Give me one moment to set things up. All right, so here we are on the TI-84 Plus. Now there are a couple of different ways of doing this. So you can do stat, scroll over to tests, and I don't think every calculator has this, but some of you might. You would select chi-squared GOF test, and then you'd enter your observed list, your expected list, and it's up to you to input the correct degrees of freedom, hit calculate, and it'll give you all the necessary information. But we're gonna do it the long way, where we're going to press second vars, which will bring us to a list of distributions. And as you can see, there's a chi-squared option. We don't want chi-squared PDF. We want chi-squared CDF, cumulative distribution function. The reason is we're looking for an area under the curve. And so I already input the values, but of course, our lower bound is going to be 6.3, and the upper bound is going to be just some large number. Again, this is corresponding to this area, this shaded region right here. All right, and of course the degrees of freedom is 5. Paste, enter, and you get a p-value of 0.2781. And a p-value of 0.2781 is very large, larger than any reasonable alpha value, and therefore we would end up failing to reject the null hypothesis. And we do not have evidence to support the alternative. So let's go back to what that context was. So the alternative hypothesis was that at least one of the 2020 proportions is different than 2018. We don't have evidence to support that. And so we have really no choice but to take this as truth, right? It's not necessarily true. Again, we maybe got like a lucky sample. There, of course, are still type 1 and type 2 errors. But at this very moment, we are, based on this one study, we take this as what is very likely true, or at least the most feasible outcome. All right. So, you know, I didn't really go into this as formally as I would if, you know, you might be tested on this information. I just really wanted to give you a general idea of how you might run the chi-squared goodness of fit test. There are two other types of chi-squared tests. They are the chi-squared test of independence and squared test of association. So the thing is, those two are very, very similar. There's one minute difference between the two, which is kind of hard to pick up on. Anyway, that'll sort of be the discussion in next video, how we might run this test in different situations. So the summary though, when do we use a chi-squared goodness of fit test? Think about what we were given. Two important pieces of information. We were given a population distribution. So the 2018 population distribution of this categorical variable. And then we were given a sample distribution of colors. All right, so we are comparing our sample to the given population. And whenever you're doing that with categorical values that are not success failure, then you would use a chi-squared goodness of fit test. Another thing I didn't do was give you the conditions for this test. I'm going to run through them very, very briefly, but I'm not going to write them down or anything. I'll just mention them. The conditions are not very different from all of the other types of tests. Of course, we want a randomization condition. We also want something called counted data. So the observed data you should be able to either read it as counts, or you should be able to convert it into counts. So here we were just given straight up counts, but you might be given proportions of your sample, but you need to somehow be able to convert it into counts. And the reason we need, of course, counts is, well, if we didn't have observed counts, we wouldn't then be able to calculate the test stat. So we do need counted data, or the ability to convert our observed data into counted data, and our sample size assumption. So we want, this is very similar to, I guess, the success failure condition in some way. We want to make sure that our expected counts are all at least 5. So each of these values in this column, let me use blue here. We want to make sure that each of these is at least 5. And in this particular case, that is true. Of course, if it ends up not being true at some point, proceed with caution and carry out the test and maybe observe the results with sort of like a grain of salt. All right, ladies and gentlemen, that is all. Of course, if you have any questions, never hesitate to ask, and talk to you soon.